and then build model and learn from them to create smart software engineering tools. So of course, MAPS is one of the core event to talk about these kind of applications. So I am imagining all of you will be interested in that. So with this background, in particular, today I will talk about software artifacts, defects, repair, etc. So software can be represented in many ways. Of course, we know all about source code. When we compile source code, we can see it is transferred to binary code, and then finally, once you start executing the code, you have the execution process. So not only that, software comes with all other metadata. For example, bug report. We have a lot of code comments, descriptions, as well as specifications like a lot of pre-post condition, high-level properties, program configuration, etc. And so traditionally, when we do not run software, PLSE, security researchers, both from industry and academia, of course, they build static analysis tools to analyze all these kind of code-related data without running the software, and that turns out to be very effective for bug detection. Similarly, there are tons of dynamic analysis tools. A lot of you probably have heard about fuzzing, one of the leading kind of campaign for vulnerability detection. And what we showed, along with as a community, we showed along all these different aspects, machine learning models can help. For example, in my lab, we built different language models for improving static analysis. There are multimodal classification tools for dynamic analysis, and many more. Like in all these things, we can apply AI. So in today's talk, I will primarily focus on mathematics and architecture. I will talk mostly on static analysis part, and slightly I will incorporate how we can use code execution to improve it further. So let's take a step back and try to see why all this machine learning based approach is at all possible while we are detecting bugs and fixes. The reason is that we all know software is very repetitive. And not only that, it turns out the kind of bugs developer introduce as well as fix them is very repetitive too. So for example, here I took some real code taken from popular Java code in the GitHub, and you can see the red leaf there, and clearly they are not very scalable, as well as it requires a lot of domain knowledge and expertise. So here comes the importance of machine learning, because machine learning tends to learn well from noisy patterns and can generalize well. However, when we are applying machine learning to software engineering data, that comes with a lot of challenges. So I would like to highlight some of the challenges. So first, as we all know, software data or code has rich syntactic structure. So as you can see here, this small file code, and I show the abstract syntax tree of that file code, which is like pretty deep, complicated tree. Then it also comes with a lot of static semantic properties. For example, this code, the block of code, it apparently looks good, right? Like with a lot of for is going on. However, if you look carefully, there is a small bug where if.elements, where if is a keyword in general purpose language, and if we don't know that if is a keyword in my language, then this kind of, though apparently syntactically, apparently looking code which is good is syntactically incorrect. Also, there are contextual correctness. For example, here again you can see apparently pretty good quality as you can see here, f is my function, and now in this if comparison, I said lim equals f, which usually does not make sense. I mean, it can if it is like void pointer, void function, things like that. But usually this is like you are not comparing a whole function body with a code. Similarly, another one, see here the function expects boolean to return where I am returning now. So this all kind of contextual correctness is important. Finally, let's see some execution properties. Here I am showing a simple natural language. My favorite fruit is banana and my favorite fruit is orange. If I know the sentence, I know that, okay, just by syntactic parsing, the fruit's value is banana and orange respectively. However, if I show a low-level code like this, move ex edx or move ecx edx, we don't know what the values look like. So even if I know the semantic of move is to move the value from second operand to the first operand, if I don't know how they are executed, we won't be able to know the exact value of these registers. And also code is a little bit cannot tolerate ambiguity. So if say there are small introduction of token, like say here x less than 0 is changed to x less than equal to 0, the code can be totally different. Also, if you can have a very different code but semantically refactored, semantically correct code, though they are not exactly similar looking, they can be semantically correct. And finally, as I said, there are a lot of metadata of different modalities. So with all these things, like to understand code representation or capture code representation correctly, we have to understand the tokens, understand their structure, semantic and execution properties, as well as metadata. So in this talk, I try to shed some light with these two applications, translation and generation model for bug fix and bug classification, where we would leverage all these different properties of code. But again, definitely these properties are not limited to only these two applications, obviously. But I would like to remind us that, these properties are very important for code representation, and we should leverage them more and more as we are growing towards more bigger models. So with that, first I will talk about how we can use more like encoder-decoder kind of models for code edits and bug fixes. Here, we'll particularly leverage token, obviously, and then structure and metadata. So I will start with some very basic model. We used this model, or we wrote this model a couple of years back, but I thought, before we go to bigger model, let's have a kind of basic background of simple models. So it turns out code editing can be captured as a sequence-to-sequence task, where my before edit version or the body version can go to a machine learning model as a previous task, like as a sequence, and the output, the after edit version of the code will be or the bug fix code will be the targeted code, so source and target, right? And my other colleagues, Tufano et al., they used a very simple encoder-decoder model to realize this task. In fact, they are the first one. They showed that a very simple RNN-based encoder-decoder task can actually present code edit or capture code edit. However, so basically here what is going on, your encoder is taking this sequence of tokens, then and the decoder is again generating the updated version or the edited version of the sequence of tokens. However, the problem with such a simple token-based model for sequence-to-sequence task is that it generates a lot of syntactically incorrect code, and obviously, so those codes are not very usable, right? And very like obvious syntactic incorrect code they generate because they do not have syntactic nature. They are not ever of syntactic nature. So for that, we basically try to generate syntactic correct code. So what we did, say, remember each piece of the statement can be represented as my abstract syntax tree. And so for each piece of code, we first represent it as abstract syntax tree. And then we try to translate the abstract syntax tree of the after edit code. And finally, we generate the corresponding statement or token sequence of that from that after edit tree. So it becomes more like a hierarchical tree translation kind of encoder decoder. Now, capturing or translating this kind of tree turns out to be non-trivial, especially it requires, I mean, it is not, it does not have a lot of speed, I mean, it suffers from speed. So what we did is basically we represent each of the tree node as a context-free grammar. So now my abstract syntax tree can be represented as my context-free grammar, and then the tree structure, tree translate task essentially becomes a translation task of sequence of grammar rules. So as you can see here, my before edit code in the left-hand side is a sequence of grammar rules, context-free grammar rules. After edit is also sequence of context-free grammar rules, and we can simply translate this sequence of grammar rules. So once we have this sequence of grammar rule, we can basically form the tree by traversing this grammar rule in the leftmost derivation way. So once this is done, so now we have the tree. However, we are still not done because we have the edited tree, we need the statement. So now this generating the tokens becomes slightly easier because we have the types. So for example, here you can see if I want to generate the equal sign, I have the equal type. So we can simply generate the keyword equal to use the type. Things become slightly more complex for identifiers. So what we did here, we use scope analysis. So given I have a particular type in my abstract syntax tree, we only try to generate those tokens which are in the scope of the generated code. So for example, here at this location super.equals, I have only three things at my object that can be in my scope, which is object and temp. So we can then rank according based on the probability given by the grammar. So with this kind of hierarchical tree modeling, we tested it with, at that time, they were fairly standard data set, which is the generic CODIT data sets from GitHub, some pull request data sets. And we did fairly well from the state of that times of the art models. We had something, pretty good improvement. And also we can successfully fix some of the defects for the bugs. 15 bugs without any help and 10 bugs partially. Again, they were state of the art at the time of when we wrote the paper. So this was good, this was encouraging, but one of the problems with some small task-specific model is that they are targeted for particular tasks. So for example, the tasks I just presented, they are targeted for syntactic error code fix tasks, right? So they tend to learn a lot of spurious features, And also there are a lot of repetitive work because you will create one model trained for one particular task and then another model for another particular task. So this is not sustainable. And the community is trying to more focus on the pre-training paradigm where given some code, we will first learn generic code representation from a given code without any objective. And then we can transfer that knowledge for the specific task. So for example, given I have a binary code, you can, or a source code, you can first learn a generic code representation. Usually people use a language model, a masked language model, and or other. We will discuss a little bit soon. And then once we have this generic representation, we can transfer them for other tasks, specific tasks like say bug detection, bug fix, and many other tasks. So the good part about such pre-training paradigm is that they are generalizable, so that reduce the risk of overfitting. They are adaptive, so once we have a large pre-trained model, we can use with small training data for different downstream or fine-tuning tasks. And also they are cheap in the sense that for the large pre-training, you don't need a lot of manual annotated data. They are usually like self-trained, right? So the annotation effort is rather small. So with that, again for code editing or bug fixing, we designed this PL bar. So this is a large-scale pre-trained model with encoder-decoder architecture, where pre-training is, we did the pre-training in an unsupervised way. So our encoder goal was it should be able to read code, understand code, and reason about the error in the code so that it can learn robust representation. And the decoder's goal would be to generate code and learn code editing or coding patterns. So for that, we had a correct code. We took a randomly chosen correct function. Then we inject noise and create some noisy code pattern. The way we created noise so that its syntax, we break the syntax of the code. And now the decoder takes such noisy code and the decoder learns to correct that code. So in that way, we are teaching PL1 how to construct good code from the noisy code. So in this paper, we use token masking, token deletion, and token infilling, basically replacing and replacing a good token with a bad token for generating the noise. And here our training objective is to generate the whole code so that we can learn syntax implicitly and learn coding pattern. We did that in for Java and Python, which are multilingual setting, and also we took natural language from Stack Overflow. So for downstream task or fine-tuning task, we checked along many different applications like code summarization, generalization, translation, classification, etc. And it turns out that PL1 actually does pretty well across all tasks. It reached either state-of-the-art performance or comparable performance. So then we also noticed in particular bug fixing tasks, we also noticed that bug fixing comes with a lot of hints by developers often. So for example, here you can see there was a bug in the code marked in red line that new JSON.chart whatever. So basically it missed JSON object is empty, that check. However, the developer guided that fix problems which occur when the resulting JSON is empty. So if the developers give such guidance, we were thinking whether we can leverage that kind of metadata. So we use PLBART along with this kind of metadata which comes as the natural language text and design the multimodal learning framework. So we found that PLBART with such multimodal learning framework, we can improve 34% with respect to CodeBART and 30% with respect to CodeGPT. So overall, it seems that the up to 16% improvement can be done with multimodality training. So with that, so far we were discussing that we can use different code specific properties to improve code generation. So I will slightly try to cover like whether how for code classification tasks, how we can leverage such code specification properties. Again, our application in this talk is vulnerability detection, but this can be applied to many such code classification tasks. So as we know, probably most of us know, there is this code classification task nowadays are BART kind of model, which is a pre-trained transformer encoder. And these pre-training are task agnostic masked language model. There are several variation and improvement of BART that is proposed, a lot of us use it. So, at a high level, BART kind of, you have a code, it masks one of the token, and the masked language model, which is usually based on transformer, its job is to predict the masked token. So in this way, these kind of models are trained to capture the token, understand the token sequence. So what we did along with that, we also tried to predict the type of the token. In that way, we should be, our hypothesis is that we should also capture structure because basically the type is coming from the abstract syntax tree. And also, we generate some semantic error code variants. So we took our original code and then by some functionally equivalent transmission, by say changing the variable name or changing say while loop to for loop, reordering some independent statements, we are creating this functionally equivalent code. And we are also adding some very small structural noise to or structural wrong pattern to inject bug. So we have these two kind of positive and negative sample. Functionally equivalent is the positive sample, and when we are injecting bug, which is the negative sample. And then we use the contrastive learning basically. So my goal will be that the positive sample and original sample will be taken, together in the representation space, while the positive and the negative samples will be farther apart in the representation space. So in that way, using contrastive learning, we train this model. While generating the body patterns or negative contrast, we intentionally try to inject very small changes so that to make the task more hard, so that the original code and the negative sample will still be structurally very similar. However, their functionality will be different because it's semantically incorrect. So with such aware contrastive learning setting, we built this code, and we found that our baseline, which is like these standard models, I forgot which like PLBART, CodeBART, we have bunch of baselines there, which are typically trained on large model. However, which is say with pre-training size 20 gig. However, this scope which is only trained on 865 megabyte data can actually slightly outperform the state of the best baselines that we have taken. And more interestingly, if you slowly increase the data size and train this scope, but still much smaller size than the state of the art, we can significantly outperform the baseline. So the thing I am trying to emphasize here that when designing our pre-training objective, if we design it more like a code property aware fashion, we even with smaller data size we can beat the state of the art. So and then finally I will very quickly cover even with such static properties, for certain software engineering tasks, we may not even reach this. I mean, we may not even have a very good success because there we actually need more semantic knowledge or more basically execution aware kind of semantics. So for example, here I showing you two binary code which are taken from the same binary code. They are semantically similar, but they are compiled for two different architecture, and just by looking at it, you can see they are syntactically not similar at all. Similarly, this again semantically similar code. They are compiled with different compiler optimization flag, and you can see the code. See the pattern of the code, the static pattern of the code are very different. Same for if you introduce obfuscation. So here also we get very different looking code. So for this kind of, if you are looking for this very for applications which actually want to reason about execution properties, sometimes only static analysis may not be very helpful, and in such case you need more trace values. So in this kind of pre-training, we basically took the instruction set for binary and then run it with microtraces. By microtrace, we basically took a function, randomly initialized the function parameters and memory values and run it, took some traces, and then we create a pre-trained task which can learn the operation semantics of each of the binary instructions. And then the task, we basically try to match the binaries that are semantically equivalent, though they are not syntactically equivalent. So this is my fine-tuning task to match binaries. And it turns out that such execution effect error pre-training task can improve the binary similarities by up to 14. Then on average, the model is effective with around 15% effectiveness. So again, for the lack of time and
connect this one?
cost. So again, SA artifacts have a lot of similar patterns with subtle variabilities, and medium learning based model can be very.
So the internet here dropped. Can you?
Hello.
Hi. The internet here dropped. So like, can you repeat like the last 1 minute?
Can you tell me?
Go back one slide,
Next
please.
slide, should I repeat from?
Yeah, Baisakhi, go back one slide, please. One more. Let's start from here, yeah.
Okay, sounds good. Okay, so I was talking about certain kind of tasks where we need more execution-aware semantics of the code. And here we design a pre-training tasks, which along with instructions will also take the trace values. And when we are capturing the trace values, we basically micro-execute the code. What does that mean? We basically take any function, sample any function, and randomly initialize its parameters and try to execute it. So again, this kind of micro execution will not give us the global semantics of the code or instructions, but it will still give us the local semantics, like say a plus b equal to c. If a's value is 2 and b's value is 3, then equal to is 5. That kind of very small local semantics. So we designed again pre-trained model that can understand these instruction as well as local semantics. And our fine-tuning task, we can transfer this pre-trained model for binary similarity detection, where I have code 1 and code 2 in the representation space. And then my fine-tuning task is that if they are semantically equivalent, then basically in the representation space they will come together. So what we found that this kind of execution-aware pre-training can give pretty good boost in different binary similarity matching tasks, up to 14.3% for cross-obfuscation similarity matching. And I am not going in details, but we looked into many different security applications, including vulnerability detection, reverse engineering, malware analysis, forensics, and we found pretty good improvement with respect to the state-of-the-art along all these paths. So again, the main focus of this talk, I wanted to kind of reiterate that building ML models are great, but they can give really good boost if we design them to take advantage of different code properties at many levels. So yeah, there are structural and similar semantic properties, type information, API, dynamic traces, previous path histories, a lot of such code properties. There are plethora of software engineering applications where we can apply them, like generate code, detect bugs, detect performance degradation, predict cost and whatnot, like many more. And there are different artifacts available, source code, binary, traces, text, different metadata, email, question answer, etc. And we encourage all this data to build smart tools. And with that, I will like to thank all my students and collaborators. The upper row are mainly the students who did all this work. And with that, I would like to take any questions.
Okay, thank you. I think we have time for a couple of questions.
Sure.
Did anyone say anything on Slack yet? Okay, so over here. Okay, so while no one else is asking questions, I'll ask a question. In the first part of your talk, you talked about learning to transform rules using which the trees generated, because you said that learning directly tree transformation is hard. But a lot of recent work is actually showing that you could just on the fly constrain the decoder to generate syntactically correct fragments. Did you try
So
that?
yes. Yeah, at that point, again, this was a much smaller model. We started with, capturing this tree-to-tree translation. But then actually sequence to sequence translation is always faster than tree to tree translation. So one of the thing we realized that if you can capture the tree in a sequential manner, and there can be many such manner, but we use the context-free grammar, then the translation is faster, and then you can basically like on the fly. So that was one of our goal to basically to use the power of sequence to sequence model, but still use the tree properties.
Okay, specifically my question was, instead of doing this work in the space of rules, you could directly do this work as a token sequences and simply constrain the decoder to not generate bad, invalid syntax. But we can take that off that. Let's give a chance to someone here
Sure.
who might have a question. Yes, please. Please introduce yourself and speak louder because I don't think the people up there is.
Hi, my name is Iris. I'm from the University of Pennsylvania. Thanks for the talk. So I saw in one of your slides, or one of them, that you have worked on vulnerability detection tasks on different programming languages. I'm curious to know if you have noticed any properties of these different languages, basically how it affects the performance of models.
So, okay, our vulnerability detection task, which is this one, this is mostly on the C language. Because I mean, I think that the problem is that for vulnerability detect, the problem is that getting large-scale vulnerable data is somewhat limited beyond C. However, we use different language for bug detection, which is and they are. I mean, we did not see much difference across different language for that.
Okay, thank you.
All right. Anyone else? No. In that case, let's thank Vaishakhi one more time for the wonderful talk. Thank you. And we can get set up for our subsequent talk. Ready, are you? But this will be sent out on YouTube anyways, right?
No, but he's on the other one.
Oh,
Yeah, so what we need to do is get you to share on Gather as well. Is that possible? I can send you a link right now.
Yeah, if you're on the Slack also,
it's
there's a
1 or
link.
2 minutes, you should quickly. All the speakers who are basically here know that they will have the talk as well. Otherwise, the broadcast will not work.
Okay.
I'm sorry? Yeah. She's right there. Yes, she's right there.
Okay.
Yeah, you can take.
For those of you who are physically speaking, just so you know, those need to be logged into Gather Town while you're doing the talk, because then that will be last.
I'm not sure if it's